And let me quickly share my screen. There we go. All right, welcome everyone. For those of you who do not know me, my name is Lauren Traster, and I am the 4-H Teen and Leadership Program Coordinator here for Vermont 4-H. I just put into the chat, if you need our live captioning today, just click on the link and you can follow along to today's presentation. I'm going to ask that everyone open up your chat box. We love to just do quick introductions before we get started. So would love to know who you are, where you're from, just a way of getting everybody comfortable in this space. So just find your chat. And I recognize a lot of familiar names already, but it would be great if you can introduce yourself into the chat. We have Hitesh from Massachusetts. Glad you could join us. Who else is with us today? Henry and Margaret from Ohio. I forgot to let our presenter know that we actually get young people from all over the place, not just Vermont, but Misha's here, Jonas is here, Xavier is here. We got the leads from my favorite state of Rhode Island. Liam's joining us from Vermont. Fantastic. Keep introducing yourselves. I'm gonna keep moving on, but I want you all to keep introducing yourselves if you're just getting here. Please remember, find your name on the participant list. You're gonna show up as the first name on your list when you open it up. Rename yourself so I know who you are, because we do check names against the registration list. And if I don't see you on my list, I then start private messaging you. Who are you? I need to know. So go into the participant list, rename yourself with at least your first name, and at the very least, the first initial of your last name, if not your entire last name. And that helps me just match things up on the participant list. Like I see somebody is coming up as, oh, I think that's fixed. Don't mind me. Sometimes my lists don't look correctly. All right. While you're here in Zoom land, we ask that you stay muted unless you have a question that you want to ask, and you can raise your hand. Don't raise your hand in the video because I won't be able to see you, but use the raise your hand button feature, and then we can find the time to break and let you ask your question, or you can use the chat box. We love to use the chat box as ways for you to engage with our presenter, whether she asks you questions or whether you have thoughts about what she's talking about, but we really like the chat to stay on topic. If you get off topic, it ends up being really distracting for everyone who's trying to pay attention to the cafe. So just be courteous and respectful. If you choose to have your video on, and again, that's a choice, you don't have to, but if you do, just make sure that there's nothing going on behind you that would be distracting. Don't move around your house, just stay in one place. And then I know you're all going to be engaged and participate fully, but that's the best way to learn. And I know tonight's topic is going to be really interesting. So before we get to that, I do want to tell you about the rest of the Science Cafe schedule and then some other events. So this is our last virtual cafe for this school year, but we do have 2 in-person cafes coming up. One on April 9th, which is on the biomedical engineering for tissue health. It's going to be really interesting. And then our last one on May 14th is Mission to Mars with a space engineer from Benchmark Space Systems, that is a satellite company right here in Vermont. So those both should be really exciting. They are in person, which we do at UVM, and we serve you up some free pizza while you're learning. And the in-person cafes have hands-on activities, so hopefully you'll join us for those. We also have Summer of Science, and the programs are being finalized right now, but I do know there's going to be a week-long science exploration camp at UVM. We're going to have a pet first aid workshop. We offer a Natural Resource Management Academy, which is a weekend at the Green Mountain Conservation Camp, where we bring in natural resource professionals to do various workshops throughout the weekend. We're going to spend a day with the Watershed Alliance out on their research vessel for part of the day on Lake Champlain, and then going to their fish dissection lab. And then there's a few more programs that are still being fine-tuned. So that information is going to be coming out very soon, and will be posted at the website that's posted on this slide. We also have a new program, 2 summer academies that are going to happen at UVM at the end of June, with work that goes on throughout the summer. It's called Agrotech Innovation Academies, and the focus is agri-science, where each academy is going to be focused working with faculty in their lab on their specific topics related to agri-science. Very hands-on, very cool. You sleep in the dorms for the week. Go to this website and learn more about the program, because it is entirely free. If you get accepted, you do have to apply. So lots of opportunities coming up. I'm really excited to share those with you. And let's get to tonight's cafe topic. Tonight, we're going to be learning about what can a quantum computer do and why should you care. Our presenter is Mary Beth Ruskai. Let me tell you a little bit about Beth. She is a retired mathematical physicist who worked in quantum information theory. Her research has been supported by the National Security Agency and the National Science Foundation. From 2011 to 2018, she was an associate member of the Institute for Quantum Computing in Waterloo, Canada. So let's all welcome Mary Beth to our Teen Science Cafe. Mary Beth, it is all you.
Okay, I'm very glad to be here. And I know that students have a lot of different backgrounds, and I don't know what your backgrounds are. So please feel free to ask questions in the chat box or raise your hand at any time. And I'll be asking you a few questions occasionally. Now I'm going to share my screen. First, I have to go to full screen view, enter full screen. There we go. And share screen. And I think it's this one. Nope, that's the wrong one. Okay. Okay. So everyone can see the screen. So, okay, here's the title. And, oh, something's wrong. Stop sharing. First, I seem to have, okay. I'm going to try start share again. So let me just see something else here. Oh no, okay, it is. Okay, so it is. Oh shit, oops. Okay. Okay, whoa, whoa, whoa.
We can see it.
Yeah, but I don't want you to see too much.
Oh, okay.
Okay, so first I want to tell you a little bit about public key cryptography. Like when you send your credit card over the internet, the encoding method is public, the decoding is secret. Now you all probably know that 15 equals 3 times 5. Can anybody tell me what the factors are for 77? You can put it in the chat box. Somebody's got it, 11 times 7. And what about 221? Anybody? Factor 221? It's a little trickier. Yeah, a lot of people have got the, oh no, it's not 11 times 11, but you're getting closer. Okay, it's 13 times 17 is what it turns out to be. Now, what about this big long number? Well, I can't factor that. I cheated by looking up some prime numbers and multiplying them together. And the idea behind public key cryptography is that the encoding uses a large number like this, and the decoding needs its factors. And you can say, well, but can a supercomputer do that? Well, actually not. It takes, as you make it longer and longer, it gets harder and harder, and it's challenging even on a supercomputer. Actually, I suspect that if it's just your credit card over the number over the internet and NSA really wanted you, they could probably do it. But if you will see that if you make it longer and longer, it gets harder and harder until it really is impractical. Okay, and I think that's basically what I said. But a quantum computer can do that kind of factoring very quickly and easily, and it would make the current public cryptography that we have insecure. However, there's also a way to use quantum particles for newer and better cryptography. So let me tell you, before I tell you about that, I'm not going to talk about this all. This is just the method that's used to encrypt numbers over the internet if anybody is interested for completeness, but I'm not going to talk about it or go through it. Now, you might say, why am I have this Mac quest? Well, suppose I want to go from close to where I live in Charlotte, Vermont, to Essex, New York. Well, if you look at MapQuest, it'll give you this route where you drive all the way down here, and it is 94 miles and takes over an hour. Or you can take the ferry across the lake, and that takes about half an hour and is only about 6 miles. So this is an example. Quantum computers are not actually, well, we haven't built any yet, although they're getting very close. They're not faster. They can't factor large numbers because they're faster than regular computers, because they use a completely different method. So for example, if you took the long car route, it would take you 75 minutes as compared to the ferry. But the ferry goes slower. It only goes at 5 miles an hour compared to 44. But because you don't have to go far, you use a different method, you get there in less time by using a different method, even though you go more slowly as you take the boat across the lake. Okay. So there's only certain types of problems that are actually solved faster on a quantum computer. And they're sometimes called promise problems, where it's like factoring, where the answers are maybe hard to find, but are easy to check. Also, as we'll see, quantum systems are basically probabilistic. So it only gets the correct answer with a high probability. Okay. It doesn't necessarily get it. You have to check it. Okay. All right. So now I want to compare polynomials with exponential growth. So let's first suppose that you want to do something, sort a list, something, and of size n, okay? And let's suppose it takes 7 times n squared number of steps on the computer, and the computer you have can do that in an hour. And now you get a new computer that is 1,000,000 times faster. Put this in the chat box. How many items can the new computer pass? It's 1,000,000 times faster, or 10 to the 6 times faster. $5 billion. Okay, let me go through it with you. Okay, so the old one took, for 5,000 items, took 7 times 5,000 squared times, and the new computer is 10 to the 6 times faster, and 10 to the 6 is 10 to the 3rd squared. So the new computer can do what's the number that is being squared. Okay, so the number being squared is 5,000 times 10 to the 3rd. So that's 5 million items, but the increase, it's not 1,000,000 times faster. That's the important thing. It's only 1,000 times faster. Okay, so you don't, just because it's your computer is 1,000,000 times as powerful doesn't mean that it can something that takes where the time is proportional n squared. What if I had changed the 7 to 23? How would the answer have changed then? Any ideas? So notice that really all that mattered for the compare, the 7 and if I had 23 would be important in the number of steps the computer actually takes. But for this type of comparison, the 7 cancels out and it only matters what it is that we're squaring. Okay. Okay, so let's try another one. And we've already done this one. The new computer is 10 to the 6 times faster. It can do 10 to the. Now, suppose that the number of steps is not n squared, but n cubed. And you've got this new computer that's 10 to the 6 times faster. How much faster? How many can the new one do? Or how much faster is the new one? Okay, well, it'll only be 10 squared or 100 times faster because you have to take the cube root of the 10 to the 6. Suppose, well, one of the things you notice that as the exponent gets up, as the number of steps needed to do something takes more and more, the advantages of getting the faster computer goes down from 1,000 to 100 times. Suppose the number of steps was the square root of n. Okay. And the new one is only 1,000 times faster. How much can the new one do, do you think? Yes, I think somebody's got it. 10 to the 6, they're 1,000,000 times faster. Okay. So this one is when you don't need, when you need a lower number of steps, the advantage to getting a bigger computer is more powerful. Also notice that the n squared and the n cubed are n squared and the square root are kind of the reverse. When it takes n squared, the advantage is only by the square root. If it takes square root of n, then the advantage is squared. Okay. Now let's go to exponential growth. And one thing I find very useful is to realize that 2 to the 10th is 1024 or roughly 1,000 or 10 cubed. That's very useful. So now instead of a polynomial, our n is up in the exponent. So if n were 150, that means it would be some number of times 2 to the 150th set. 2 to the 150 is 2 to the 10th to the 15th. And for the 2 to the 10th, I can put in 10 cubed. And so I need 10 to the 45th steps. That would be 1 followed by 45 zeros. That would be a really, really super powerful computer that could do that. Okay. Now you've got a new computer that's 1,000 times faster. How many can it do now? Well, I'll go through this one with you. So the number of steps is now 2 to the 150 times 10 cubed, okay? And 10 cubed is 2 to the 10th. And 2 to the 150 times 2 to the 10th, remember when you multiply, you add exponents, it's 2 to the 160, so it can only do 160. 10 more. So that big 1,000 times faster only gave you process 10 more items. Now suppose your new computer is 1,000,000 times faster, 10 to the 6 times faster. How many can you do now? Well, you do the same thing as before. 10 to the 6th is 2 to the 20th. So altogether, 150 plus 20 is 170. So 1,000,000 times faster only gets you up to 170. So every time you do that, every time you make it 1,000 times faster, you only gain that you can do 10 more items. Okay, if I made it 1,000,000,000 times faster, then I could do 30 more. So you're nowhere near even being able to do double the number you were before. So with exponential growth, eventually you hit a wall where getting a bigger, faster computer has a very, very small effect in what you can do. And that's why when people talk about exponential growth, that it makes it impractical. You know, a lot of times people, try to give you an impression of just how large some number like this with this zero is. But I think this reverse method, where you see once you get to a certain point, when you have exponential growth, making something say 1,000,000 times faster only lets you do 20 more, really gives you a feeling to just how impractical something is when you have a large number of items and it takes an exponential amount of time. Okay, now so I want to talk whether you're using a regular computer or a quantum computer. When you want to transmit information, usually the first thing you do is to digitize it, to convert it to a strings of ones and zeros. And for an ordinary computer, you can think of the on-off switch representing 1 and 0. Okay. Now, quantum particles, you can think of electrons as having what's called spin. They can act like little tiny magnets. And you can use spin up for 0 and spin down for 1. So that means anything you could do with a classical computer, you could do with a quantum computer. But you can do other things. Okay, you could have, instead of up and down, right or left. And the question is, well, if this means 0 and what do right and left mean? And another question is, can you represent any direction, not just right and left, but north, northwest, or any direction you wanted? Okay. All right. So a bit is what we call, you call regular computer units. A qubit is the basic unit of quantum information, and it's represented by a vector of 2 numbers, which I'll usually write with this symbol, and they add up to 1, but that's not the main thing. So the spin up, which represent, so in this, what's called a ket symbol, the 0 means I'm using this to represent 0. And that vector is the one that is a 1 and then a 0. And the down is 0 and 1. And I have plotted them here on this graph. So a 1, 0 looks like this. And then the right and left, those will correspond to 1, 1 and 1 minus 1, which I've plotted here. Now, if you look closely, you might be getting confused because the vectors don't seem to match. But since many people may not be familiar with vectors, let's look at this picture of blown up. Okay, and in the red, I've the x-axis is along here. So I've got a vector that has x equal to 1, y equal to 2. So here the X is 1 and here's 2, that's Y. Okay. In the blue, the X is minus 1.5, that's here, and it goes up 1/2. Now, I'm going to put some things into the chat and let you annotate on your screen and try to see if you can draw in the vector that corresponds. So let's start with a simple one, -1 plus
Mary
1.
Beth, I'm just going to interrupt so everyone knows how to annotate.
Yes.
If you take your mouse and look at the top of your screen, and everyone's might be a little different, but there should be a thing that says view options with a drop-down menu. You'll see that there's an annotate option. And if you click on that, it opens up the annotate feature, which gives you the ability to write on the screen. And hopefully you all can find that so that you can do this little activity that Mary Beth is talking about. Desmond, without being there, I can't help you find it. But I see others have found it. So I'm sorry if you were unable to get the annotate, but if you can put your answer on the slide. If not, just try to work on a scratch piece of paper at home.
Actually, they're not showing up on my screen. If people are annotating, it's not showing up on my screen.
I saw a couple of people. Yeah, I see a couple of people have it.
Oh, I see some things.
Yeah, people are popping up. And if you make a mark, then hit erase so that your mark is now erased. So just tell them what you want them to do. I think most people have it.
I know what the problem is. I didn't push return so that they could see my message. So see if you can draw the vector that has -1, -1. So both X and Y are -1.
Did you put something in the chat?
Yes, that's now.
We don't see it. Did you hit return?
Yeah, I did now. At first I did, before I didn't, but it's there now.
I don't see it.
Yeah, there, somebody's got it. Okay, let's
Okay.
try another one. Let me try, let me think. Well, let's just try. Okay, so now I want the 1/2 and -1.2. Ah, somebody's got it. 1/2 -1. Oh, lots of people have got it now. Okay. So in physics, when you have vectors, things like this, the length and direction of the vector can make a big difference. They can typically have a physical interpretation. Why is mine? Okay, like the, can somebody erase? I can still see the things on my screen. The arrow represents, the length can represent the size of the force and the direction. But mathematically, you could have vectors that go beyond 2 and 3 dimensions. And in fact, if you have more than 1 qubit, you need to do that. So actually, the vectors that we're using are, the arrows don't really matter because I'm always going to be using vectors of length 1. And if you go back, okay, everything is equal to 1. So really, these arrows just represent points on the circle, but if I just put a dot there, that would be a lot harder to see than the arrow. Okay, so that's the convention. And there are many applications. And so we won't be using the kinds of applications in physics where the length and the direction of the arrow make something. We're just really using points on a circle and using arrows to show that. Now, there are many different methods of using different types of physical systems to construct qubits. And at the risk of totally confusing you, I'm going to show you another method. Okay. And oops. Okay. So this is a picture of polarized light. So if you've ever had polarized sunglasses, the way that they work is that light has waves of all different kinds, but if the wave is up and down movement is in a plane, then it's called polarized. And if your sunglasses have like a vertical filter, that they only let through something that goes up and down like that. Okay. And we usually think of beams of light as waves, like it was on the previous slide, which is true, but it's actually also composed of particles. It's another way of thinking of it, and they're called photons, and they have polarization. So instead of up and down, I could use the horizontal and vertical polarization to represent 0 and 1, again with the same vectors that I had before. And I could rotate them 45 degrees, and I'll call those plus and minus. They're like my east and west. And one advantage to using these is that these directions here more closely match what you get here, which is sometimes useful for visualizing things for qubits, although it's really what's in the vector. So here we have different points on the circle. Okay. Okay. All right, so this is a summary of the notation. So spin up and down correspond to right and left. Spin up and down correspond to horizontal and vertical polarization. Left and right correspond to when you rotated the polarization axes. Okay. And for these vectors, instead of 0, 1, I'll use plus and minus. Now the question is, what does that mean? Okay, now I'll briefly tell you about the principles of quantum mechanics. We've already said that states are represented by vectors. The time development is given by the Schrödinger equation, but we don't need to worry. We're not going to do anything. We don't need that at all. And physical observers are represented by operators called matrices. And there are special numbers AK and UK that satisfy a certain equation, but the equation is not important. What is important is that if you measure this physical observable, like the direction of the spin, okay, or momentum or something, you will get one of the numbers AK, okay, and that's the only possible thing you can get. And then another equation with this vectors and the vectors that are in this equation here gives you the probability of getting that number. Now I'm going to unshare my screen to demonstrate that. Should I turn on a light? Is everything, I might have to turn on a light.
Yes, it's dark.
Okay.
There, that's much better.
Okay. And can you now see me with my hiking poles? Okay.
Yes.
Okay, now you should imagine that I'm hiking along and I've come to a river and I want to know how deep the river is, whether or not I can safely get across it without drowning. Well, one way to do that would just be to take my hiking pole. Okay. So let's, oh, I guess you still can't see this at the ground. Okay. To put my hiking pole in and see where it comes to see how deep the water is. Okay, you may have done that. Now here, if you look at these white markings, this is what I call my quantum hiking pole. Because now if I put this one into the river, these white lines are like the AKs. It's guaranteed that it will go to one of these exactly, okay? And it doesn't go to the closest one, okay? Whatever the water is, the only possible result when I test the water and put it in is it will go to one of these spots on my quantum hiking pole. And after it does that, that will be the level of the water. I don't know what the level of water was before I put the pole in, but afterwards, it's at this level that's on the quantum hiking pole. Okay, and that is one of the most important fundamental principles of quantum mechanics. And now I'm going to reshare my screen. Okay. Okay. So you have these special numbers of AK, and because you end up in the state that's associated with that number, the original was destroyed, which is why I would have no idea what the depth of the water was before I put in my quantum hiking pole. Because measuring destroys the original state and takes it for one of these special states associated with a special number, you cannot clone quantum states. And that will actually turn out to be surprisingly useful. Okay. So let's go back to our using polarized photons instead of, and one of the reasons I introduced that instead of spin. So if you have these filters, okay, light can go in all kinds of ways, but what comes out is always polarized through this filter. Now, if you have a single photon, even though it's not a wave, but just a single photon, it still has this polarization property. And it might not be in one of the states corresponding to these two filters. It might be in a different state. So it has to decide which one to go through, unless it happens to line up. And what comes out, just like here, what comes out after the vertical polarized filter has to be in that state, okay? So if it goes through a vertical filter, it has to be in this state, and it will go through with probability y squared. That's the closest I can come to an explanation of something that is, frankly, quite mysterious, and people spend their lives trying to understand it. And that was one of the reasons for introducing polarization. You could at least think of how a measurement can force something to be in only certain states. Okay, here's another thing. Because I said it can't clone. So we start with some unknown direction, okay? And somebody sends you this saying, you go in this direction to get to my house. Well, you can choose a measurement that, say, decides between north and south, like spin up and down. But then you're left in the state north and south, and you can't get any useful information about east or west. Or I could choose a measurement that decides between east and west. But now you're left in that state, and I can't get any information about north and south. So the measurement process destroys the original state. And what this means is that qubits can store much more information, okay? I mean, I could, with zeros and ones, I could just do north and south. So I could have this, some north-northwest direction. I could have any direction that I wanted stored in a qubit, but you can't extract more information. You can extract north or south if you want, or east or west, but you can't get the exact angle. Okay, and that's what makes quantum things so interesting. Now, I just want to say a little bit about vector spaces. We drew them before, and we don't need very many properties. You can add them together. One key property is if you've got two vectors in the vector space, then what you add together will always be in the vector space. And we're usually going to write them like this, as column vectors. Sometimes they're written as row vectors. And there's something called the inner product or dot product. And if you have two vectors, w, z, x, y, the dot product, you just take ordinary multiplication of the first 2, W and X here, and plus the ordinary multiplication of the second ones, X, Z, and Y. And that's called the dot product. We won't use that very much, but what's important is when that dot product is equal to 0. And we call that orthogonal, which is a fancy word for perpendicular, okay? And we had these special numbers that were associated with measurements and special vectors that were also associated with them. And it's a fact that if the numbers are different, then these special vectors are orthogonal or perpendicular. Their dot product equals 0. And only vectors whose dot product equals 0 can be distinguished by measurement. So let me do this in a little more detail for our basic examples. And, you know, I realize it's a little confusing. Here on the left, 0 and 1 represent the states. Okay, so the state we usually vector we usually associate with 0 is 1, 0. And what we associate with 1 is 0, 1. And if you multiply them out, the first two, you have 1 times 0 plus 0 times 1, you get 0. Okay. If instead I had used my plus and minus, which was I calling the things that are right and left, well, you have 1, 1, first two, and then 1 minus 1. 1 minus 1, you again get 0. And now if you look at the bottom in the polarization picture, you can actually see that they look perpendicular to each other. Okay. But if I were to instead take the inner product with plus and 0, that would be 1, 1 and 1, 0. Okay, so you have 1 times 1 plus 1 times 0, and there's a square root in front. The factor in front just makes the length always be 1. You get 1 over the square root of 2, which is definitely not 0. So if I wanted to distinguish between this red up arrow and this sort of slanted what is it? This is northwest, and this blue northwest arrow, I couldn't tell them apart in any reliable way by a measurement. Okay. Okay. Any questions so far? Okay. Okay, so let's try to give an interpretation for these plus and minuses. Well, I can write this 1, 1 as 1, 0 plus 0, 1. Okay. And I can then say plus is equal as 1 over square root of 2 of my 0 vector or state and my 1 vector. And minus is 0 minus. And that's called a superposition. And when we took the inner product, we got 1 over the square root of 2. Okay, so if I tried to measure 0 and 1 in one of these states, okay, I would get each of them with a probability of 1 over square root of 2 squared or 1/2. Okay, and you could sort of see on the previous slide, the blue was just rotated. And so I could interchange the roles of 0 and 1 and plus or minus. A very minor point, as I said, for the most part, we should think of these vectors as points on a circle, but the arrows make them easier to visualize. Because the probabilities are given by squaring something, a vector and minus v represent the same physical state. So we can only really use a half circle. The vectors in the opposite direction will represent the same thing, but that's a minor point. Okay, so now let's try some quantum cryptography. And what you want is what's called a secret keypad, or a long string of zeros and ones. Okay, and you've got some message which is also written in terms of zeros and ones. And you take the keypad, and the idea is if there's a 1, it flips the bit. And if there's a 0, it leaves it. So 0 here. And then you have a 1 here. And you get a 1. There's no flip. Here's a 1 that flips it. So it changes this 1 to 0. And here, when I have 1, 0, it changes the 0 to 1. And it's a little bit equivalent thing is to say, if you add them as go along, two zeros or two ones give you a 0, and a 0 and 1 always gives you a 1. That's, I find, an easier way to sort of go from here to here. But one of the advantages of the bit flip method is for decoding, you do exactly the same thing, okay? Because if you have a 0 that doesn't flip anything, it leaves it flips. If you had a 1, it'll flip it and then it'll flip it back. So that makes the coding and decoding easy. And if your secret keypad is very long, then your coded message just look like a random strings of zeros and ones, and nobody can get any information from it. Okay. So the idea of quantum cryptography is to try to construct one of these secret keypads. Okay. So quantum key distribution. Alice wants to send a secret message to Bob. This is a convention, I think, electrical engineers. Alice is always sending a message to Bob. And Alice uses polarized photons to send a random string of zeros and ones. And she wants to send zeros and ones, but she doesn't do it consistently with our up and down arrows. She switches between the 0, 1 basis and the plus or minus basis. Okay. And Bob randomly measures switching back and forth between these two different bases. So you might like say, okay, well, what on earth good is that going to do? Well, after they've done, they talk on an insecure cell phone. Let me go to the next picture. So here are Alice and Bob. Here's the quantum, they're sending the photons here. And they're doing measurements, sometimes 0, 1, sometimes plus minus. And then they call up on their cell phones and the whole world can listen in. And they tell which basis they used. And if they didn't use the same, if what they used didn't match, they discard that information. But when they use the same basis, okay, then they know they have to match. And so they keep that. Okay, they keep that, and people can listen in on their cell phones about how they did the measurements, but they're the only ones who know the result. And so that gives them a secret keypad. Okay, that's the really basic fundamental. So I want to stop and ask if anybody has any questions about that part. Okay. Okay. But now suppose there's an eavesdropper trying to get one of their photons. Okay. Well, the eavesdropper can only get reliable information if she uses the same basis to do the measurements. Okay. Because you've got single photon, one photon. There's no cloning of quantum states, and that's what makes this secure. The quantum principle that destroys the state when you measure it means it can't be cloned. So suppose Alice sends to Bob using the 0, 1 basis to measure, and Eve measures using plus or minus. Well, her result only matches Alice half the time. More important, if she uses this, then what she forwards to Bob will be in this plus or minus basis. And when he and Alice talk, they'll realize that they don't match and they'll discard the information. So it's completely irrelevant whether or not she got that information. If she forwards to Bob using plus or minus and he measures with 0, 1, that is, he matches what Alice did, then his result is only going to agree with Alice half the time because he didn't get what she sent. He got what the eavesdropper forwarded, which for which you only get 0, 1 with a probability 1/2. So the eavesdropper cannot get information without introducing the errors in what Alice and Bob, what Bob gets from Alice. And so what they do is they don't use the whole secret keypad. They use part of it just to compare and see if there were any errors introduced. Okay. So the way I like to think about it, if you tap a phone, I mean, you know, in the old days when people tried to tap phones and technology wasn't so good, that you could sometimes hear some static or something on the line to let you know that your phone was being tapped. But with modern technology, there are very sophisticated ways of tapping phones without, you know, having any static or anything. Whereas this kind of quantum communication, if there's an eavesdropper, okay, the physics and the mathematics guarantee that the eavesdropper will introduce errors in the system. So with this quantum key distribution, you can always tell if Homeland Security is listening in. Any question about that? Okay. So let me make some remarks about this. It's a remote procedure. Alice and Bob don't meet, but they do need to have some kind of, they don't need to, you know, meet and have a whole big code book or something, but they have to have some way of identifying themselves to make sure that somebody didn't go into Bob's room and bop him over the head and pretend to be Bob. Okay. There are several different protocols using similar ideas, and I might briefly discuss one using what are called entangled states. It has a very interesting history because there was a physics graduate student. Hey, wait a minute, I'm going to get some more water. Does anyone have any questions other than thinking they might report me to Homeland Security? Okay, so this graduate student actually used similar ideas as a proposal for quantum money, and no one would publish it. But this BB84 that stands for the name of two people. One of them is Charlie Bennett at IBM, and he knew about this work. And then when people started talking about quantum computers and quantum messages, he realized that the idea could be used for this kind of encoding. Get some more. And well, people building a quantum computer is challenging. People are working on it. Let me get some more. There are commercial devices you can buy using fiber optic cables. This technology is much, much further along than quantum computers. They're good for over 100 kilometers. Free space is actually better. Round to satellite is much better. And those devices are available. Curiously, the one that I'm most familiar with from someone based in Switzerland, it's interesting who buys it. The people that buy their devices are casinos, and they don't use them for secret messages. They use them as random number generators because of the probabilistic aspect of this. And that seemed pretty interesting. Okay, that is the main thing I wanted to tell you about. And let's see if you have questions about that. Okay. So if you have more than one qubit, which you would need to do anything, you get a long string. You actually, instead of zeros and ones, if you had pluses, that would in some sense be 0 plus 1. And when you multiply them out, you would get all the combinations of zeros and ones, which is where the quantum computer gets its power. But they get, when you get a large number, a very small probability, which means the challenge when you try to do something on a quantum computer, it's not enough to get the correct answer. You also have to make sure that these probabilities change so that you're peaked around the correct answer. Now, I did have some applications, maybe I'll just do very briefly. You have pairs of qubits. You use something called a tensor product, but I'm not going to worry about the details. So you can have 0, 0, and 1, 1 would look like this. They're very similar. And remember I said when you had vectors, one of their properties was if you added two of them together, you got something in the vector space. Okay. Okay. Well, okay. This is called an entangled state. There's no way to write it as a product. And I put the definitions in, but we don't really need them. I think I'm going to, okay. I'm just going to go. So now if you have one of these entangled states and Alice and Bob share them, okay, then if Alice makes a measurement and Bob does nothing, because it changes to the state Alice is in, the whole system is going to be in the 0, 0 state. So she knows what Bob has, even if they're light years apart. And similarly, if she gets a 1, she knows that the combined system is in this state. And entanglement is one of the more, even more mysterious things that has lots of applications. You could even imagine a different key distribution based upon this. I had some other things. One last one was what I call Bell's cell phone puzzle. So you wake up in the morning and your cell phone has these 3 red, green, and blue coins that are spinning around, and it says, flip me. Oh, why it doesn't equal faster than light communication. Because when you do the measurement, you destroy something. It's actually, that's actually hard to explain. Okay. Okay. That's actually hard to explain. And you know, people say that Einstein said God does not play dice with the universe, but he really was not very troubled by the probability, but by the probabilistic aspect. What he was troubled about was exactly this thing, that once you have an entangled state, no matter how far apart they are, you have these correlations and you get this information called it spooky action at a distance. You get this information. Now, of course, there's a challenge to prepare a state like this, and then Bob and Alice take it away and are light years apart. But they can't exploit that information in any reasonable way. Okay, I'll just, so anyhow, they can't use their cell phone until they pick a coin and then they win something. And it seems fair, but what they discover, if they pick the same color, one wins and the other loses, but they can't exploit that. Their phone is locked. They can't exchange messages. So you can't call your friend and say, I picked blue and lost, so if you pick blue, you win. But what's interesting is not that. It's that they pick different colors where you would expect absolutely nothing, you know, no correlations. If they pick different colors, they both win 3/8 of the time. And they both lose 3/8 of the time. It's not like you would expect 1/4, 1/4, 1/4. And I think I won't go through why that is an anomaly. I'll just say that these entangled states, by sharing an entangled state like this, you write it heads, tails, you can explain the fact that when they pick the same color, they get the opposite result. Okay. The other is much harder to explain. But basically, instead of, you have 3 different, a red, green, and blue measurement, and different ways of choosing those. Each of these is perpendicular, so they're each a valid measurement will give you that. And okay. And there's some further reading. I have to say these are probably fairly advanced for middle school. The book by David Berman is a delightful collection of essays, some on quantum mechanics, and the title one is just worth the price of the book. David Wick has a very nice history of how these ideas of quantum mechanics developed. David Merman has a book on quantum information science. He writes very, very well. And these 2 people work in quantum information theory, and they also teach at 2 colleges in Ohio and that are noted for their education. And they've written an introductory text, but it is for undergraduates rather than high school students. So I will stop, I think, sharing my screen.
Oh, thank you so much. Before we get to any of your final questions, I'm going to just quickly put up a poll. One simple question, if you could answer it. We just like to know, did you learn anything by attending tonight's cafe? So 1 is on the low end, 5 is on the high end. And we'll just keep this open and think about any questions you might have for Mary Beth. I know we're over time a little bit, but we do want to make sure if you have any questions for her that you have the opportunity to ask them. I'm going to just wait for several more of you to answer the poll, and then we'll get to your questions. Okay, I think we got just about everyone. All right, I'm going to close the poll, and feel free to put any questions you might have in the chat or raise your hand, and we'll call on you to unmute yourself. I'll give it a minute because I know there's always a slight delay. And it's also okay if you don't have any questions. I know this was a big topic, and it does seem like you all learned a lot by coming. So I'm going to stall just for a few more seconds just to see if anything comes in the chat. If not, then let's all, go ahead.
There was something in the chat. Somebody said that they thought they had been successful in building a quantum computer. That is not true. What both I think is Google, and there was somebody else, some people in China, they built systems that were that proved that quantum systems could do things classical systems could not, things that would take this exponential time on a classical computer could be done efficiently. But these were special purpose devices designed for a particular and somewhat artificial problem, that they demonstrated that you could have quantum systems where something that would take this exponential growth in possibly long time on a classical computer could be done very efficiently, but they weren't general computer machines that you could program them to do different tasks. So they were special purpose quantum devices, but they weren't like a full-fledged programmable quantum computer.
Great. Well, let's all thank Mary Beth for her time tonight and teaching us all about quantum computers. I couldn't follow anything, but I know these guys did. I mean, I don't say that you're a wonderful teacher. I have just been out of mathematics for a very long time. But I will say I was able to follow along in the beginning. I actually could calculate the the machines and the different rates. So I was very proud of myself with that.
And I was going to say, I'll make a handout version of my slides and send it to you if you want to post it or send it to the students. There was another one who said, do I think they'll have to invent new coding languages for future quantum computers? People are still looking at the kinds of problems that you can solve for which they'd really be useful. One of the things that a quantum computer can do is if you want to sort of find an item in an unsorted list, like a reverse phone book lookup, which you can now do very quickly on a, their devices built for that, where something is not in alphabetical order and you want to find something, it can do that in the square root of time of what a classical computer do. So if you've got 2 billion items, that can give you a very fast speed up. So there are particular problems. I think they're still finding out what kinds of things a quantum computer really has a practical advantage for. And then they will pair them, I think, with classical computers to do things that classical computers. So it will be a back and forth. And I think if the people, they could now, if you were satisfied with 100 qubits, they could build such a device. But what the experimenters are really concentrating on is how to build something that you can scale up to a really, really large number. I don't know if that answered the question. I think.
Love it. Well, thank you so much. And thank you all for joining us tonight. Maybe we'll see some of you in person at our cafe on April 9th or the one on May 14th. But thank you all for joining us and have a wonderful night.